this chapter is very important chapter, but I will give the minimum requirement you need to work for the next chapter. So you don't need to consider the whole chapter because it's very tough chapter actually. So the things which I want to study is that the statistics of the number, the average of the number of the states. So let me to check the exact title of that. Occupation number, or average of the number of particles in state or in the energy E. So in E, this is the average of the particle which they sit or they have the energy E for the different gas. So we will consider the three types of the particle, fermions, which I talked before, and the bosons, and the Maxwell and classical particles. So the approach is that we want to calculate again the number of the state, possible states in the system by considering the quantum features. So the one which I talked before about that, about the exchange of the particles, so about the wave functions and the exclusion principle for the fermion, and to consider all of them. So we will start by the case, by some definitions. Just so V is as usual the volume of the system. So and you know that each energy level is occupied normally by more than one particle. So we have a degeneracy, or what we call it GI, which is a very big number actually, because each energy level can be occupied by, you can have several energy levels with the same energy in the whole ensemble. So GI, we call it the number of the levels, or I don't know, degeneracy state, number of levels in each cell. So the picture is the same as the before, so there is nothing special here. Just we have the cell 1, 2, 3 in your ensemble, cell I. So each one has the energy levels, the same energy level, because they are considered as the same systems, each one. And the GI is the number of the level, or what we call it occupation numbers in each cell. For example, here is G1, G2, and GI. And you know that both of the quantity, the number of the energy levels, and also the occupation or the number of the particles in each energy level, all of this quantity are big. So GI is actually a big number. It's related to the number of the state of the energy in the system. So, and the things which here is very important is the quantity. We call it this Ni. So Ni, which is I started from 1 to the number of the particle in the ensemble, N, it's called it the distribution. Is like the distribution of the grade, distribution of temperature, or any other distribution in mathematics. So this is a distribution of the particles over energy EI. So this is a very abstract part, so I want to very quickly just review, because you needed to know that how we find the grand partition function for the boson and fermion and these things. So The condition which we have here is that, as usual, this finally the total number of the particle of the system is n, but the interpretation is different. Ni now is number of the particles which sit in the energy level Ei. So sigma Ni is n. The other thing is that the definition of the average. So the total energy of the system Ni Ei is E. This is almost the same as we used it before, just that interpretation is different. This chapter and next chapter will be about the statistic, as I told you, statistical occupation number. I want to know that if energy level E1 has the N1 particle with this energy and the N2 particle E2, so you can make an average from here, average Ni. I want to know that what is the dependence of that to the temperature and the other quantities. We are going to find this is some type of the microscopic quantity. Before we talk about the pressure or something, but we are interested to find the Ni. The average Ni is the average of the particle energy level Ei. So what we call it omega was, omega was the sigma, all the possibility which you have it here. Number of the microstat. This is a number of. I'm talking about the microcanonical first, but any number of the micro or canonical or grand canonical states associated to the or with the distribution anyway. Distribution statement. So this is about the whole ensemble, huh? So this is related to it should be related to the number of the possibility which you have here, the number of possibility which you have here, number of possibility. So Wi actually is just notation. You can write like pi Wi, so it means that this is for cell number 1, cell number 2, and these things. So the question is that what is this Wi? So you can calculate each of them. You know this now. You know just that. This is exactly that. I give you the total energy for this cell, and you can tell me that if each energy level can be occupied by one particle or more than one particle, or just by two particles with opposite, fermion or boson something. If you know which kind of the particle are here, so you can calculate the Wi by the factorials, by the countings. If the number of energy levels are few, and if the number of particles few, you don't need to use the factorial, you just can count by hand. If there is a big number, so you need to calculate that by the factorial, by combination of mathematics. So actually, what is the Wi? Wi is the number of distinct or different ways for distributing Ni particles. Particle means any type of the particle, fermion, boson, or Maxwell particles, among the GI levels. So as I told you, this G is related to the number of the states in the system. 1, 2, 3, 4, any of them. So you know how you can distribute n particle in the GI box, but you need to know that how many particles can sit in each box. So you need to know that the particle have any problem together to sit in the one state or not. So for example, if they don't have any problem, so we call it the system bosonic. So bosonic is the system which, as I explained it in the last lecture, they can sit all and they can occupy all in the same energy level. So in this case, you can that will be the number of the number of the whole possibility you have to distribute Ni particle over the GI energy levels. Still, sigma Ni should be N. So for the fermion, this is a Wi. So for one cell, so if you want the value for the whole system will be pi I 1 to N is W. So it's very complicated. This gives you the total number of the waves for distributing some amount of the energy over the whole ensemble. So I mean, you put some energy here, some of the particle can sit in the first part of the system, and they give you the number of possibility given by these equations if you know the number of the levels. And therefore, you can repeat that for the different cells, so this will be the total possibility you have. So the next step will be, and you can do that for the fermions. For the fermions, there is a thing that, as you know, each energy level cannot be occupied by more than one. If there are two particles, they should have some different spin or different other quantity, mainly the spin. So for Fermi-Dirac, Wi for Fermi-Dirac particle will be Gi factorial Ni factorial Gi minus Ni factorial, and still W Fermi-Dirac Ni will be pi I. Yes. So in the two cases, at least now you know how is the form of omega, because for omega you needed to sigma over this. Sigma over the some multiple expressions. And for Maxwell, W I will be n factorial pi Ni factorial I from 1 to n, but you needed to consider this factorial which comes for the Gibbs paradox or for the counting problem. So the real value will be, if you multiply this 1 over n factorial to that, and the W and I will be sigma I 1 over pi Ni factorial. So all of them are very complicated actually. And okay, and we needed also to Gi plus it's Maxwell particles, they are actually super bosonics, so they really are not distinguishable. So, and they don't have any property like the spin or something. So this will be the number of the ways to distribute the particle. So the next step is that write the omega and make omega minimum with respect to your parameter. So the parameter which we have here is the one which we are looking for, that is Ni, the number of the particle in the energy stated EI or epsilon I is the one which we are looking for. That you know, the variational technique was that we make this quantity, it's related to the entropy actually, this is related to the entropy. Variation of Ni minus beta variation of Ni EI. These are two constraints we have. The constraint is that we fix the energy and we fix the number of the particles. So if you do the variation, so you will find some type of the extremum, minimum, maximum for the system. Ni will be Gi, which, if you set A0, this is will be the Maxwell, E minus 1, this is will be boson, and for A plus 1, it will be fermions. What we did is that we didn't calculate this minimum or maximum 3 times. We just introduced one parameter, we call it A. If you set it A0, you will get the distribution or W for the, if you set it 0, you will get the W for Maxwell. If you set minus 1, you get W for boson, and for plus, you get for fermion. So this is the external value which gives you the maximum to this quantity. And if you that was, you remember, that was the Gi was the number of the energy levels of degeneracy in each cell degeneracy. And Ni was the number of the particle in energy EI. So occupation number. This is, we call it occupation number. It shows that how many particles are occupying the energy level. This is a very strange relation because it gives you some exponential of the energy. You never can say easily that, for example, which energy state can occupy by more than one particle or that, because you don't know energy is positive or negative. So this exponential, what is this? This is the number of the, I told you, this is the number of the particle can sit in the energy level EI. And this is a total, like each energy can, each particle can sit more than one time in each energy level, each particle. Each particle can sit, have more than one time in the each energy level. So this is some kind of probability actually, like you have a 5 over the total, so it looks like the probability. So if I want to find the average Ni, and one thing I want to tell you that this is actually now this Ni, you can set this Ni inside the W, and so you will get entropy. So entropy will be K ln W Ni sigma K ln sigma pi Wi, and you have what is the Wni. Wni for each one we calculated was factorial like here. Yes. So from this entropy you can find the pressure just by the simple thermodynamics. So it will be of course you can, this alpha, you know, that appear here, it's e power alpha you can set as the parameter, we call it z, velocity, so it's related to that. Z is e minus alpha. Alpha was minus mu k over kt. So this is a general partition function for any type of the simple gas. I mean, no interaction for the gas or some things, and by taking into the account all the quantum features like the Pauli exclusion principle in the fermion and these things. So